Hi, thanks. Yeah, as stated, I'm Philipp. I'm working as a solution architect at Centaur, and I want to talk to you today about how we can use TRex for CGNAT scale testing. So, first, the presenter doesn't work. Yeah? Okay. So, how did I even end up in this situation? We wanted to test Juniper's SRX solution for CGNAT, and there we had a device that had a throughput capability of up to 400 gigs. So of course we needed to generate those 400 gigs in stateful traffic. But the challenge with that is our existing load generator wasn't able to generate 400 gigs of stateful traffic, since we mostly use it for layer 3, layer 2, or in protocol testing. So we needed to find a solution. Okay, we looked around, we researched a bit, and then we chose TRex. TRex is an open traffic generator. It is backed by Cisco, but you can use it as you will, and it emulates servers and clients. The best thing about TRex, though, is that you can run it on off-the-shelf and widely available hardware. This includes x86 servers and for example, NVIDIA or Mellanox NICs. The only thing that you have to keep in mind here is that you need to use NICs that support the right DPDK feature set. This is because TRex does use DPDK to achieve the high throughput and high session count that you need to test those bigger devices. So TRex also has some operating modes. They act quite differently. I will get to those later, but for now, there's the STL, STS, and advanced stateful mode. Good. This is a lightning talk. I can't go in depth about TRex, how TRex works, but I do recommend looking at the DENOG17 talk of Pim van Pelt. There, he spent about half the talk talking about TRex, or the FOSDEM talk of Hannah Holm. A quick run through about the different modes that TRex can run in. There's the stateless mode. This is focused on router or layer 3 switch testing. It's packet-based and it works like ostinator. So everyone that knows that basically knows how this mode works. There's the original mode, which was stateful. This was focused on NAT and firewall testing. So it had a limitation. You could only really test NAT if the application does look into layer 1, 2, 3, and 4, but not everything past that. And the other limitation is a lot of features have been deprecated in this mode. This, for example, sadly includes all NAT-related features. What is the solution? The advanced stateful mode is there. It's basically like the stateful mode, but you can emulate layer 7 data, for example, Citrix or HTTP sessions. And it has a better automation API and is able to support devices that interact with your application data. For example, load balancers or load balancers that do encryption of loading. Okay, quick run through about how the advanced stateful mode works. You have a full PCP stack per thread that you assign to a source and destination port pair. This is based on BSD 4.4 Lite. It's now been modified quite a bit, but this enables you to emulate layer 7 data and have all the built-in error handling that a TCP stack provides. So ramp down, ramp up, it's all handled by the stack. And of course, as every good testing solution should, you can provide values for jitter, latency, or drop rates that will be introduced. As you can see on the right side, there's a quick overview of how the communication works. Your simulated apps talk to the TCP stack, which then reads and writes from the DPDK buffers. Okay. If we want to test, we of course need to define our traffic. For this, there are two approaches. You can first define a list of PCAP files that have a capture of a client talking to a server, and TRex then will learn your TCP parameters, like an MSS, the window size, and it will take over the application data that gets transmitted in the payload, and will rewrite everything like the IPs and basically the IPs. You'd provide the list with how many connections per second you need. And the second option is manual layer 7 emulation. Here you can actually define the payload data yourself, either as a string or as a byte string in Python. And you then again provide a list of how many connections do I need, and TRex translates the IPs how you need them for your port pairs. Okay, so now we basically know how we define our traffic and how modes work in TRex, we get to how we can actually run our testing. Of course, you can just start the test, sit there, watch the error counts, and see if it's fine. But this is quite tedious, quite error-prone, and isn't really a lot of fun. So can we automate this? Of course we can. There are two approaches. TRex comes by default with a non-drop-rate benchmark. This originally was introduced for the stateful mode, stateless mode, but got support for the advanced stateful mode later. Here, you can extend it via plugins if you want to modify the error handling, and your plugins can run before your iteration, during your iteration, and after your iteration. And it uses a binary search algorithm to find the max multiplier. So you start with the min and maximal, it goes in the middle. It's binary search, but not really search, right? The second option is just build the script yourself. You can use the full API implementation, and this is the way that I did it here. Okay. You can see the topology. We had a server connected with 8 times 100 gigs to a QFX 10K. This was just used because it had a lot of 100 gig ports, nothing special there. And all our DOTs connect to this. Okay. First, the script that I wrote, you need to provide it with a min multiplier, a max multiplier, a duration, a traffic profile, and your error tolerance. I will get to why we need an error tolerance later. The min and max multiplier, again, I used for a binary search-like method to find the right multiplier. So we run this. We run the first iteration in the middle, see if it's fast enough, or if we have too many errors. And after that, depending on if we see a lot of errors in the packet or not, we continue with a higher or lower multiplier. The error detection here just looks at how many packets did I send and how many packets of this had errors. Okay. And of course, we need to log all the results so that we can later analyze and visualize them. Okay. Of course, I did some testing for 3 Juniper devices, and I brought some results. The tests here were done with a duration for each iteration of 10 minutes, and an error percentage of 0.1%. Keep in mind, the throughput that you see here is an aggregate of client and server-side traffic, and the traffic pattern is quite heavy on large packets. So the SRX1500 was able to produce about 8.88 gigabits. The SRX2300 was able to do a bit more than 37 gigabits. And then we have the outlier, the SRX4600, which actually has a PFE in it that the handling can be offloaded to, which is able to do 389 gigabits. Yeah, if you use an iMix, subtract about 10% of those results. Okay, yeah, as I said, express path on the SRX4600 is a huge benefit. I have some lessons learned. Getting an error percentage of 0% is nearly impossible. This is stated in the TRex docs, and this is also the reason why the non-drop rate test from TRex uses 1% by default. This was a bit too high for my liking, so I used 0.1. So you need to really keep in mind if you use multiple sockets that you map the right NICs to the right threads. Otherwise, you overload the inter-socket connection, and your throughput just plummets. And getting more than 200 gigabits in ASDF mode is really hard. If you ever try this and struggle, just split your NICs in 2 servers. It will really help. Okay, that's it. If you used TRex before, if you want to use TRex, or if you have any experience with TRex, please talk to me. I want to know what you've done or what you're looking to do. Thanks.
Thank you.